Hello everyone, welcome back to Mana CS Classroom. In our previous videos, we discussed several code optimization techniques used by compilers to improve the efficiency of generated code. Today we are going to learn one of the simplest yet most powerful optimization techniques used in compilers, that is Peephole Optimization. By the end of this video, you will understand what is peephole optimization, why is it needed, and the different types of peephole optimizations with easy examples. Suppose I ask a student to take a book from the shelf and place it on the table. The student does it. Immediately, I ask the same student to put the book back on the shelf. After all this effort, where is the book now? Exactly where it started. The work was performed, time was spent, energy was spent, but nothing useful happened. Many compilers generate machine code in a similar way. The generated code is correct, but some instructions perform unnecessary work. Peephole optimization identifies such situations and removes them. In simple terms, it makes the generated code smart. Not all compilers generate highly optimized code immediately. Many compilers first generate a straightforward version of the machine code. This initial code is correct, but it may contain unnecessary instructions. After code generation, the compiler examines the code and tries to improve it. One important technique used for this purpose is called peephole optimization. The word peephole comes from a small hole through which we can see only a tiny portion of a room. Similarly, the compiler does not inspect the entire program at once. Instead, it looks at a small group of consecutive instructions. This small viewing window is called a peephole. The compiler slides this window through the program and checks whether a better sequence of instructions can replace the current sequence. Let us now see the formal definition. Peephole optimization is a local optimization technique. It examines a small sequence of instructions and replaces them with another sequence that performs the same task but more efficiently. The important point is that the output of the program must remain unchanged. Only the implementation becomes better. Let us understand the characteristics. First, it is a local optimization technique. It focuses only on a small portion of code. Second, it uses a small sliding window called a peephole. Third, it improves execution speed. Fourth, it reduces program size. Finally, a compiler may perform multiple passes, but one optimization may create opportunities for another optimization. So there are 6 important peephole optimization techniques that we will study one by one. Now let us imagine that the compiler becomes a strict auditor. Its job is simple. Whenever it finds unnecessary work, it immediately removes it. The first place where it starts checking is redundant instructions. Let us start with the first optimization technique, redundant instruction elimination. The word redundant means unnecessary. Sometimes the compiler generates instructions that perform work but do not actually change anything. Such instructions only consume execution time. Peephole optimization identifies these instructions and removes them. Consider these two instructions. The first instruction loads the value of a variable into R0, variable A into R0. Immediately after that, the second instruction stores the same value back into variable A. Let us think carefully. Did the value of A change? No. The same value was loaded and stored back. Therefore, The second instruction performs no useful work. So, optimized code load A, R0. Here important condition is optimization is safe only if both instructions belong to the same basic block. So next, eliminating unreachable code. Let us move to the second optimization, elimination of unreachable code. Unreachable code refers to statements that can never be executed during program execution. Since such code will never run, keeping it serves no purpose. Consider this example. The goto statement immediately transfers control to label L2. Here, go to L2. The control transfers to label L2. As a result, statement 1, statement 2 are skipped completely. No execution path reaches these statements. Therefore, they become unreachable. Since the two statements can never execute, the compiler removes them. So this reduces code size and simplifies the program. Next we have flow of control optimization. The objective here is simple. Reduces unnecessary jumps. Every jump transfers control from one location to another. Too many jumps increase execution overhead. Therefore, compiler tries to simplify the control flow. Here the program first jumps to L1. Immediately after reaching L1, it again jumps to L2. The first jump is unnecessary because the final destination is already known. So instead of two jumps, the compiler directly transfers control to L2. So this reduces execution time and improves efficiency. So consider this situation. If the condition is true, control goes to L1. Otherwise, another jump sends control to L2. So the compiler can reverse the condition. It can reverse the condition and eliminate one jump. So this is called condition inversion. See, if you see in the original snippet, the condition was x less than y and there were two go-to jumps. If you just invert the condition, instead of writing x less than y, if you write x less than or equal to y, x greater than or equal to y, then you can avoid one go-to. Okay. Next, algebraic simplification. Compiler can also use simple mathematical identities. Adding 0 does not change a value. Subtracting 0 does not change a value. Multiplying by 1 does not change a value. Dividing by 1 does not change a value. Therefore, these operations can be removed completely. Reduction in strength means replacing a costly operation with a less costly one. For example, multiplication by 8 can be replaced by a left shift of 3 positions. Similarly, division by 4 can be replaced by a right shift of 2 positions. Shift operations are generally faster than multiplication and division. Suppose processors provide special instructions for frequently used operations. These instructions are called machine idioms. Instead of using multiple instructions, the compiler replaces them with a single specialized instruction. See, here we have load x into R1, add 1 to R1 and store the R1 value back into x. It is indirectly saying add 1 to x and store the value of x to back again x. So instead of writing these three operations, so we can simply write increment x. Indirectly increment x equals to x is equal to x plus 1. So let us summarize today's discussion. Peephole optimization. Peephole optimization is a local optimization technique. It examines a small sequence of instructions and replaces them with a faster or shorter equivalent sequence. The 6 important peephole optimization techniques are redundant instruction elimination and unreachable code elimination, flow of control optimization, algebraic simplification, reduction in strength, and use of machine idioms. Although it is a local optimization technique, it significantly improves the quality of generated code. In the next video, we will continue our discussion on code optimization techniques used in compiler design. If you found this video useful, do subscribe to Mana CS Classroom and share it with your friends. Thank you for watching. See you in the next class.